So we finally come to the Carnot cycle. It's the first completely reversible cycle. As such, it's made up of 4 reversible processes, each one of which would take forever to accomplish, but this will give us a limiting case. So the first process, it operates in a piston cylinder device, and the first process is to have the gas above the cylinder, or above the piston in the cylinder at temperature TH, whatever the high temperature is. And we're going to allow the piston to move to the right and the gases to expand, doing work, but transfer in energy from a thermal energy source already at TH so that the temperature of the gas remains constant. So this is reversible isothermal expansion. Because there's some heat transfer, this would literally take forever because there can't be any difference in temperature, therefore there can't be any heat transfer. But that aside, that little detail aside, we'll allow this to continue. So this would be a reversible isothermal or constant temperature expansion process. The next process from state 2 to state 3 is a reversible adiabatic expansion. So what we're going to do here is put insulation on the top of the cylinder, get rid of that thermal energy source temporarily, and allow the gases to continue expanding, going from a temperature TH down to TL. So this is called reversible adiabatic expansion. We're allowing very slow expansion of the gases. Again, this would take forever because no expansion of gases is completely reversible, but that's okay. So reversible adiabatic expansion from TH down to TL, and the piston does a little more work for us. This is good so far. We've gotten work out of the first process and out of the second. And then from state 3 to state 4, now we've got to get back to where we were. So we're going to start putting boundary work into the system, compressing the piston from state 3 over to state 4. But we're going to have a low temperature sink at TL, the same temperature as the gas, to reject the waste heat into. Just like the first process and second, this would take forever in reality, but at least we're not, we're giving a nod to the fact that we have to throw away some waste heat. Finally, we'd have our last process where we put insulation back on the cylinder head and compress the gases, putting work into the system from TL up to TH to end up back where we started. So this process, the cycle, consists of 4 processes, and they're all completely reversible. So this would be our Carnot cycle heat engine. Since it's reversible, we can simply run the process in reverse, right? We can go, just run all the processes in reverse, and if you notice, now the Carnot cycle is rotating counterclockwise, whereas before it was clockwise. So this is a work-consuming cycle, and it's bringing in thermal energy from a low temperature sink and pumping it into a high temperature, well, from a low temperature source to a high temperature sink, but originally it was a low temperature sink and a high temperature source. But we could reverse it, right? Now, there are some principles we learned from the Carnot cycle. The first is that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one if they have the same 2 temperatures to work between. And the efficiencies of all reversible heat engines operating between the same 2 reservoirs are the same. So it doesn't matter what type of reversible cycle you come up with, it will be the same efficiency as the Carnot cycle. So to prove the first Carnot principle, which is that reversible engines are better than irreversible ones, if we could make them, then, or more efficient, then we have to somehow show this is true. So let's start by assuming the opposite. Let's assume that, well, that's wrong. We could make an irreversible engine that is more efficient than the reversible one. The key is that the reversible engine is literally reversible, and when you run it forward, you can run it as a heat engine, but if you run it in reverse, you can run it as a refrigerator, and everything will be exactly the same. It's just the direction of the flows will be opposite. So you see that on the right-hand side with a reversible heat engine that can operate as a heat engine, pulling in QH, producing reversible work, and then rejecting QL, reversible, to the low temperature sink. And you see the dotted arrows indicating the same device being operated in reverse. But we're going to assume, for the sake of argument, that the irreversible heat engine can actually produce more work, that the amount of heat output that it produces and throws away is less than the amount of QL that the reversible heat engine throws away. Okay? So the amount of work produced by the irreversible heat engine would be greater than the amount of work produced by the reversible one. So that's what we're going to assume. Now we're going to be careful and size these two so that they're both pulling the same amount of heat either to or from the high temperature reservoir. So QH in both of these two, the reversible and irreversible, are the same values. Okay? And what we're going to do is reverse the reversible heat engine because we can, right? So we'll operate it as a refrigerator, and what we'll do is allow the irreversible heat engine to drive the reversible now refrigerator. And if you think about it, if our assumption's correct and we could do better than reversibility, then the amount of work produced by the irreversible heat engine will be more than the work consumed by the reversible heat engine. So we'd have a net amount of work coming out of the combination of the two. Since we've reversed the direction so that now the reversible heat engine is a refrigerator, it's pumping QH up. So we got QH up, QH down. They just cancel each other, right? So no flow there. But we've found something that seems to produce a net amount of work with no heat flow to the high temperature reservoir. And since we've assumed that the irreversible heat engine is better, more efficient than the reversible one, then the amount of heat it's throwing away is less than the amount of heat going up into the reversible refrigerator. Therefore, there's a net flow into the system, and we end up with figure B. Now you notice figure B just shows the difference in the heat flows from the low temperature reservoir to the two engine, and it shows the difference in work either produced or consumed between the two, the heat engine, the irreversible one, and the reversed refrigerator. And what do you notice about this? Hopefully what you notice is that the combination of the two breaks the Kelvin-Planck statement of the second law. So this proves that irreversible heat engines will never be as good as reversible ones. Of course, we can't build reversible ones. And when I say good, I'm measuring good in terms of efficiency. Okay? So this is proof of the first Carnot principle. You can actually prove the second by replacing the irreversible heat engine with a reversible one, and then assuming they give different amounts, and again, you'll break one of the two statements. So if we have a reversible heat engine A and reversible heat engine B, and they're operating between the same two reservoirs, they will have the same efficiency. And so this gives rise to the idea of a thermodynamic temperature scale, something not based on the freezing or boiling point of any substance. The second Carnot principle implies something really, really important. It implies that the thermal efficiency of these devices is a function of the two different reservoir temperatures. Well, what does that function look like? Do we need to take the natural logarithm of the sum of the two temperatures, or is it some polynomial form? Is it something easy like that? Well, no, it's neither of these. What does the function look like? Well, let's derive that. Let's figure it out from logic and reason. Remember that thermal efficiency is 1 minus QL over QH, and we can apply that to reversible heat engines as well. Reversible heat engines do not have 100% efficiency. They just have the highest theoretical possible efficiency. Well, how does that efficiency, that highest thermal efficiency, depend on these temperatures? Because after all, the one doesn't depend on the temperatures. Therefore, that ratio of heat flows, QL over QH, must be some other function of TH and TL, because that's the only thing that can change in the thermal efficiency equation. Well, we can set up three reversible heat engines, as you see in the figure, with reversible heat engine C having efficiency 1 minus Q3 over Q1. So you see the heat flows, it's the ratio of the heat flows across it. And we've got two heat engines in series with one another. The waste heat from heat engine A actually drives heat engine B. There's an intermediate temperature T2 there. It's not the same as the temperature T1 of the thermal energy reservoir at the top, or the low temperature reservoir T3 at the bottom, but it's there in between the two. Since the reversible heat engine A and B are reversible, and they are heat engines, we can write the thermal efficiency as 1 minus the ratio of their heat flows as well. And we're going to size these carefully so that heat engine C brings in Q1 in the same amount that heat engine A brings in Q1. Now obviously the ratio of the heat flows has to be a function of the temperatures across these heat engines. So we just replace the ratio of the heat flows as some function across the temperatures of the heat engine. So pulling all of that to this slide, just notice that from a pure algebraic standpoint, algebra just says, look, you're dealing with fractions. Q3 over Q1 equals the product Q2 over Q1, Q3 over Q2, because the Q2, that intermediate heat flow, will cancel. And this has nothing to do with thermo. This is simply algebra, right? This is, in fact, it's not really even algebra. This is just fractions, right? So the numerator and denominator on the right-hand side, the Q2, Q2, will cancel one another. And that makes sense. But what that means is that we should be able to multiply whatever that function is for heat engine A and heat engine B. We should be able to multiply those two functions together and get the function for heat engine C for all of this to be consistent. Now, one way to get things to cancel like this is that the functional form has to be a ratio of maybe some other functions that only depend on the variables themselves. Because notice, what we're really doing here by canceling out Q2 is canceling out T2, right? How do you cancel out a whole variable? Well, the only way to do that is if the numerator depends on one variable and the denominator depends on another. At least that's the easiest way to do it. Okay? So then the functional form of all of these would have to be the same because they're all just reversible heat engines. So the functional form of each one of these would be some ratio of the functions of the independent variables. So this would be consistent. It would make sense, right? Because we could take those now G of T ratios, plug them in, and sure enough, the two would cancel, and we get a functional form that is consistent. It would be, again, a G of T3 over G of T1, and that would make sense, at least, for reversible heat engine C, and all this would be reasonable. The simplest functional form we could take is just G of T is T itself, and in that case, QL over QH for a reversible heat engine would be TL over TH. And this is the way it is. This is what we've discovered. This is the way this works, if you will, is that the ratio of the heat flows for a reversible heat engine is equal to the ratio of the temperatures. Now, you got to be careful with this. It's an important result, you know, that the thermal efficiency of a reversible heat engine is 1 minus TL over TH, where TL and TH are the temperatures of its high and low temperature reservoirs respectively. But you need to not miss this. You got to be careful what temperatures you use here. You can't just plug Celsius into this. It won't work. You have to plug in absolute temperature units. So Rankine or Kelvin go in here, but certainly not Celsius or Fahrenheit. You should find this equation in the back of the chapter. It's probably the most important equation of the entire chapter. And it's what gives us our limit. It's what tells us the best we could ever hope to accomplish with any heat engine ever. Okay, so it's because it's, you know, all this reasoning we've gone through, we've been consistent mathematically. We believe that heat won't flow from cold to hot, even if we build a clever machine to make it do that, unless that machine has some work input. And if all that leads up to this result. This is just reasoning from that point. We basically walked across several stones very carefully. They supported our weight. We didn't get our feet wet in the creek, and we're on the other side to something that is very important. So heat engines' maximum efficiency can simply be calculated by taking 1 minus the ratio of the temperatures across the heat engine. So if we have a low temperature reservoir at 300 Kelvin, a high temperature reservoir at 1000, a reversible heat engine would have an efficiency of 70%, because 1 minus 300 over 1000 is 70%. Irreversible heat engines will have lower efficiencies than those, and it would be impossible to make a heat engine with a higher efficiency between these two limits. It simply can't be done. And the reason it can't be done is because heat won't flow from cold to hot. And you could say, well, that's not what I'm trying to do here. I'm trying to allow heat to flow from 1000 degrees down to 300, well, not really degrees, but 1000 Kelvin down to 300 Kelvin. That may be so, but you can only extract a certain percentage of that heat as work because of the nature of thermal energy. That's really what we're getting at here. So the farther apart we can have those two thermal energy reservoirs, the better, because look, if we vary the high temperature reservoir's temperature, you can see that the thermal efficiency goes up as the temperature goes up given a constant low temperature reservoir. And usually the most common thermal energy reservoir we use for ejecting waste heat is the atmosphere. Now, if you think about a heat engine like something on a space probe going out, a nuclear power plant, it has to reject waste heat because nuclear power doesn't use that nuclear power directly. It actually operates some type of thermodynamic cycle where there's waste heat that has to be thrown away. How do you get rid of it? You got to figure out a way to do it. Well, in space, about the only way to do it is to radiate it out, and so that's what they do. But anyway, the point is, the higher the temperature difference, the larger the efficiency of the heat engine. So this gives us this idea that thermal energy has a quality. It's more valuable. It's worth more. It can do more if it's at a higher temperature because we can extract a higher percentage of it as work. On the other hand, we can talk about Carnot refrigerators and heat pumps. Remember, we can reverse the Carnot cycle. If that's the case, we end up at the same place where the ratio of the heat flows across it are equal to the ratio of the temperatures. And instead of writing the coefficient of performance for a real refrigerator or heat pump, where we can replace the ratio of the heat flows with TL over TH. If we do that, then we get the coefficient of performance for a reversible refrigerator or air conditioner and a reversible heat pump device. Now notice that, again, this limits the coefficient of performance to being a function of the temperatures of the high and low temperature reservoir. And all this seems really abstract. As a matter of fact, my heat pump is running right now, so let's talk about that. What is it doing? Well, what it's doing is it is extracting low quality thermal energy from the outdoors for free, which I like, taking it, pumping it up to a higher temperature and putting it in my home. Now, a lot of people don't like heat pumps. When heat pumps were first introduced, this principle of efficiency was understood, this performance was understood, and so what designers did is they tried to minimize the difference in temperature between the source and the ultimate sink. In my case, my source is outside, my sink is the air in my home. Okay, and so what they would do is put air out of the vents that was at 90 degrees, 85 degrees, something like that. Warm enough to heat the house for sure, but if you stand over it, it just feels like cold air blowing on you because we human beings have water on our skin, and as we stand over a register like that, we feel the air coming out, it feels cold because it's pulling energy away. The water is evaporating off of our skin, and so we sense heat leaving our body rather than coming to our body, and we're like, oh, this is cold air coming out of this register. I didn't want an air conditioner, I wanted a heat pump. I wanted a nice blast of warm air. Well, modern day heat pumps don't shoot for such a lofty goal. They instead put air out of the register that it's at a higher temperature so the occupants of the house can feel more comfortable. So they're less efficient than they could be, but honestly with today's designs they're more efficient than the heat pumps of yesteryear that should have been more efficient because they were minimizing that difference between temperature. So you can sacrifice a little bit of the thermodynamic theoretical efficiency and use, instead of a reciprocating heat pump, use like what mine has, which is a Copeland scroll compressor instead, which is much more efficient. It doesn't have as much irreversibility as inherent in its design, and so it just performs better. It doesn't require as much work to compress the refrigerant as a reciprocating compressor requires. And so it can afford to lose a little bit in generating higher temperature air, and of course they're using a different refrigerant and modern oils and things that again reduce irreversibilities of friction. And so all of this makes for a heat pump that is pretty efficient, and you feel like it's warm in the house because, yeah, you probably don't want to stand over the register. It's not all that warm when the heat pump is working, but it's warm enough you can tell, yeah, this is warm air coming out of the vent. So this is the way that we can determine the limits of operation. As a matter of fact, my heat pump has a SEER rating of either 16 or 18, I don't remember now. So it's not too bad. It's not as good as some of them today, but it's certainly not a slouch. Not near as bad as the heat pumps originally introduced. And the maximum efficiency it could ever have is governed by that equation right down there. If you know the outdoor temperature, that's TL. You know the indoor temperature you want, that's TH. And those temperatures determine the limit of efficiency. They determine the minimum amount of electricity I'll have to pay for in order to warm up my house. So the maximum efficiency of a heat pump or refrigerator can be calculated. So for a refrigerator, if you have a refrigerated space at 275 Kelvin, which is a reasonable temperature for a refrigerator, and you have a warm environment like a kitchen at about 300 Kelvin, that's only 25 Kelvin difference, but it's the ratio of those two that matter. And so the maximum reversible refrigerator coefficient of performance in that case is 11. That's the best you can ever do. If you go back to that coefficient of performance equation for a refrigerator, you'll see that the math works out this way. Irreversible refrigerators will not do as well. They will have a lower efficiency, and it's impossible to make a refrigerator with a higher efficiency than that. Now I hope the questions I posed at the beginning make some sense. We're going to answer the questions: what is the most efficient heat engine, refrigerator, or heat pump we could theoretically make, and what does the efficiency of these devices depend on? I hope you have a little more insight now, and you realize that the temperature of the source and sink make a big difference in the efficiency of the devices. It's not something typically that we can have a lot of control over, but there are ways to do it. For example, if I wanted to make my refrigerator more efficient, and I've thought of doing this, I haven't done it yet, but I've thought of it, I could take the coils and in the wintertime expose them to the outdoors, right? Because then the temperature sink is already cold. It would be very easy for the compressor to run and compress the refrigerant because the heat already wants to flow from inside of the refrigerator to outdoors, assuming that it's below 0 degrees outside, or below the freezer temperature too, which is probably negative 20 or 25, something like that. But I could get away without the whole system then, right? As long as it was cold enough outside, well, my food would stay frozen without any trouble. Of course, I'd have to try and prevent the milk from freezing somehow. I wouldn't want it to get that cold. But you can see that the temperature of the source and sink should reasonably make a difference. How could we increase the efficiency of your car's engine, for example? The low temperature sink is the atmosphere. You're not going to change the atmosphere's temperature, right? That's just not going to happen. I know that global warming is a concern. I know that there are seasonal variations. You as a human being can't just dial up the thermostat tomorrow. If we could, we'd probably get out of this winter stuff pretty quick, and we'd probably dial it back in the summer a little bit. But we can't, right? So whatever the temperature is of the atmosphere, that's just the sink temperature. That's the best we can do. But do we have any control over the temperature of the thermal energy source? Well, what is it in your car? Well, when you put the gasoline in the combustion chamber with air and you burn it, at that instant you have high temperature, hot, high pressure gases, right? Those gases are going to expand doing work. The higher the temperature of those gases can be, the higher the theoretical efficiency of the engine, the higher efficiency the engine could reach if we design it well and reduce irreversibilities. So this has not been a wasted consideration, right? Even though irreversible processes aren't possible, but they give us the limits. Well, at least now we know where the limits are, and we've got some insight on what to actually attack. I think it's a shame that a lot of people really believe in free energy, and they spend much of their life pursuing it, when some logical analysis is fairly convincing in showing that it's not possible. I wish that those people, which are usually technically inclined, would learn a little bit here and put their endeavors into something that actually could, because this points the way to increasing efficiency. If you could make better materials that could take higher temperatures, okay, to make engines out of, that could be helpful because we could increase the combustion temperature, right? If you could figure out a way to reduce irreversibilities, well, the free energy people already know about friction, and that's fine, but there are other irreversibilities too. All of them degrade the system's performance. Is there some way to make pistons move a little slower so the gas expansion is not quite so rapid? As a matter of fact, that's one of the tricks taken into account in my car. I drive a diesel car, and it's got I bought this particular one because it has 6 speeds. I wouldn't buy an automatic transmission, but I love manuals. So I've got 6 gears. Well, I can cruise down the highway at 50 miles an hour or 55 or 60 and be turning about 1,000 RPM. That's still moving pretty fast, but it's not moving as fast as 3,000 RPM, right? It's moving at about 1/3 that speed. That gives the air-fuel mixture more time to expand. So that's one way of doing it. Another way, I wish I could find it. There was a ship I read about once. I believe it was built. I'm going to go look for it after this lecture. But this ship, the idea was, it was back in the days of steamships, and the idea was that we want the steam to have plenty of time to expand. We want it to expand slowly. So why don't we make pistons that are, huge diameter and let them rise and fall very slowly? As a matter of fact, they move so slowly that people could set tables out and have dinner on top of these pistons. One of the sides was exposed. Now, how they kept it from getting too hot, I don't know. So that's why I'm not sure the ship was built. I believe it was when I read about it. There's a lot I read about in college, and I wish I had written down references, and I don't have them anymore. But anyway, the pistons move so slowly. Well, why would you make a piston move so slow? I want the car to go. Well, if it's big enough, it'll still produce plenty of work and power to drive the car, the engine, the ship, the whatever it is. If it's practical, so obviously not practical in a car, might be practical on a ship. Why would you do that? Well, to reduce irreversibilities, right? So understanding this, we at least have a chance. We have a path forward for hopefully doing something practical and improving the efficiency of work producing and work consuming devices.